We can see from these examples above that the vector valued function r of t is actually giving us the position of the rock or object. And that's exactly what we're going to use in order to be able to expand upon the Calc 1 ideas of velocity and acceleration, etc. that we had. So r of t is our position function. So at any given time t0, the location of the object is pointed out by the vector r of t0, where r is a vector, which isn't too big of a deal. We've seen the points is not a big deal when you substitute a particular value in. Then the graph of r of t is the path or trajectory of that object. It's going to have horizontal and vertical motion, like this example right here. So if it has horizontal and vertical, then that's two-dimensional. But if it has horizontal, vertical, and then a sideways motion, like there's a crosswind or something like that, that will be three-dimensional. All right, now the usual relationships between position, velocity, acceleration will still work because we already know how to find derivatives and integrals with vector valued functions, just like we did from Calc 1 with regular functions. So the velocity is a vector, and it's the derivative of position, but position is r of t. Speed is the magnitude of the velocity, which is the magnitude of r prime. And acceleration is a vector unto itself, and that would be the derivative of velocity, which of course is the second derivative of position. So those forms that we learned in Calc 1 for how velocity, speed, and acceleration and position all relate to each other still hold. So Newton knew what he was up to when he came up with this stuff. All right, so let's derive our basic formulas for projectile motion in 2 dimensions. So we're only going to think about this in 2 dimensions for now, because of course 2 dimensions is easier to think about. So we have a projectile given both horizontal and vertical velocity. The object moves in 2 dimensions. Suppose our object is thrown from an initial position. Okay, so let me just draw this right here. So we have an initial position, which is over here. Let me give it a blue piece over here. So we're going to have an initial position, which is right here. So at time t equals 0, we have x0, y0. That's why it's got the little 0 subscript. And it has an initial velocity, so the motion is going like this, right? It's going to hit over here. So there's your motion, so it's going along that way. So that's your position function. And the initial velocity, you can see it's got those 0 subscript, is the vector that's pointing off that way. So that's your velocity vector at time 0, which a lot of times we abbreviate it, v of 0 right here. And that would be u0, v0. So they tell us that we're throwing this projectile or shooting it or whatever, but the only force acting on it initially is gravity, right? So it has gravity once the object is released. So we need gravity. Now gravity, the abbreviation for gravitational constant is g. So the acceleration vector is real easy to figure out because you have no acceleration in the x direction, so that's 0. But you know gravity, but gravity pulls downward, so it's negative g. I'm assuming the gravitational constant is a number, so I'm going to make a little note over here. Physics classes will sometimes make g negative, in which case then this would be positive g because g is negative. Anyway, so for our purposes, we're going to let g be, and it's an approximation. If you're in metric, it would be 9.8 meters per second squared. If you're in imperial system, i.e. the English system, gravity is about 32 feet per second squared on Earth, I should say. Other planets, on moons and things like that, every massive astronomical body would have its own gravitational constant, but those are the two for Earth. Oh, that's 9.8. Sorry, my point. Okay, so that's just something to note. We're not actually going to use it for this problem because we're trying to come up with the generic formulas, but that's something to note for future. So I consider G to be a positive number. Again, your physics instructor might say it's negative, in which case, it doesn't really change how any of this works. Okay, so there's the acceleration. Done. All right, now let's go up a step. To find velocity, of course, we need, right, acceleration is the derivative of velocity. So velocity is the integral of acceleration. Fundamental theorem of calculus, right? So I want to integrate 0, negative g with respect to t. Okay, so that would be the integral of 0 would be just 0. And the integral of negative g, well, that's a constant, so it would be t. Plus some constant vector. Now, here's where things get fun. Because we know the initial velocity right here, this constant vector could be used to find that initial velocity. So this right here is going to be u0, v0, right? The initial velocity. And therefore, velocity would be equal to 0, negative gt plus u0, v0. Let me do that in orange. So velocity is equal to u0, comma, negative gt plus v0. All right, now what about position? Okay, well, position, r of t, is, I'll start writing over here, is the integral of velocity. Okay, so that's the integral of u0, comma, negative gt plus v0 with respect to t. All right, so that's u0 t. That's a constant, right? u0 is just some number, so I would throw a t onto that. And then this will be negative 1/2 gt squared, because you'll have to add 1 to the power. This is currently to the 1 power, so you add 1 at 2, so it's a half, plus v0t plus some new constant vector. So I could call these, like, this one's c1, right, because that's for velocity, and then this one's c2 because that's one for position. It doesn't really make any difference. They're just not the same. That's all you need to know. Okay, but we know this vector, right? This is the initial position, which we know is x0, y0. So that means that my position vector is u0t negative 1/2 gt squared plus v0t plus x0, y0. And by the way, I'm able to pop these in there and just do that because we all know that this will be polynomial pieces. So these component pieces of these vectors are polynomials. If they were transcendentals, we'd be having different issues, but that's not how projectile motion works. So we're able to just pop those values right in there, substitute them in. And so that means that r of t, which is what we were really looking for, is equal to u0t plus x0, and then negative 1/2, that's gravity. So this is the x motion direction at the beginning, right? So that's the velocity, if you will, in the x direction, times t plus the initial x position, negative 1/2 g t squared, there's gravity, plus v0. Actually, you know what? Wait 1 second. This is the initial velocity. This is the initial velocity times t plus y0. So you can see your initial velocity is right there. It's tucked into the t components of these. And then your initial position is right there. It's the constants that are added on. And then gravity only affects the y because gravity pulls you toward downward and only downward. So that's that piece right there. So in the absence of any forces other than gravity, this is how this will work. So this is, in other words, wind resistance. In the absence of wind resistance and friction and things like that, R of t will be equal to u0t plus x0 negative 1/2 g t squared plus v0t plus y0. Period, the end. So what this means is that ignore friction, ignore wind resistance, you know, all that kind of good stuff, depending on, usually for something like this, it'd be wind resistance that you're thinking of. And I will say that the other ones are so important, I think I'm going to box them as well, even though it wasn't specifically asking. That's how acceleration works, always. And this will be how velocity works, always. And those lead to that position, vector valued function.